Okay, guys, welcome back. So here we are, another week, back at workload chemistry. So today we're going to start chapter 5, and as you may recall, last week Thursday will be the one of our quizzes. So it'll be a good review because we had a couple of chapters now. So I think it's perfect time to kind of test you guys on what you know. And then as you know, I changed the midterm date, so it will be most likely on November 19th. So in a couple of weeks. So I hope to get through all of the quantum chemistry stuff at least, and I think I'll test you guys on chapters 2 through all the way through to maybe chapter 11, which is the end of quantum chemistry for this course. But without further ado, let's just hop right back into it. So so just one more announcement I want to make, that the homework is going to be due. So homework 4 due tomorrow. Oops. We're going to be due tomorrow. And I think I spelled that wrong. I can't spell today. Yeah, that's definitely wrong. At 11 p.m. All right, so make sure you do the homework. Is worth points, is worth 20% of your grade. So those are what I think are easy points. So make sure you do them in a timely fashion. Extensions will not be granted unless they're either, glaring technical issues or you have a valid excuse with proper documentation. Otherwise, I cannot really grant an extension. Okay, now let's talk about chapter 5. So we're going to bounce between looking at some lecture slides and talking here on the tablet, just because there's some helpful pictures that help depict what I'm talking about, and it will save time for my less than par drawing to kind of convey what is being said on the slide. But don't worry, for slides that have like lots of text, I won't really show them. I'll just write them. I'll just write what I think is most important. So let's talk about the atomic theory. So we're going to be talking about the nuclear model of the atom today. So the nuclear model of the atom. So when we talk about the nuclear model of the atom, we assume that the atom is composed of a nucleus, and that there's subatomic particles or particles within something that are that make up the nucleus, that holds the nucleus together and gives the atom its kind of identity. But first, we're going to talk about Dalton's atomic theory. So first, we're going to talk about Dalton's atomic theory. One of the earliest theories of the atom, which states the following: each element. Hold on, I think I started my clock. Oh, I did. Okay. Each element is made up of individual particles called atoms. And the thing to know about atoms, they are, whoops, sorry. Let me just turn this on because I don't want to accidentally draw something. So atoms are indivisible. So that means we cannot break them into smaller portions or smaller pieces. Atoms are indivisible. So all atoms of one element, are identical. So what we mean that they're identical. That say I have one atom here and another atom here. That means that they won't be different in a way like, oh, this atom has more like electrons than this other similar atom. They're all identical in every way, is what I like to put it, or is how I like to put it. Okay. So then on the contrary, all maybe not say all, but atoms of one element are different from atoms of any other element. So, and then we say that atoms of one element can combine with atoms of other elements to form chemical compounds. So I like to use the water example. One oxygen atom combines with two hydrogen atoms and they form the water compound. So this is all part of Dalton's atomic theory and how elements combine, how they're all different from other elements, and that you cannot divide atoms. They are the smallest unit of matter. Okay, so that is Dalton's atomic theory. So let's move on. Okay. So this when we say they're not divisible, atoms cannot be created nor destroyed, and all atoms of any given element, they have the same properties. So they are the same in every way, like I said, including mass. But atoms of different elements, they'll have different masses because they're unique, right? So they shouldn't have the same mass of, like, say, another element. Because that would mean that they would be the same, but in fact they are not, because they have different identities, and we can identify different elements based on their atomic mass. So when we have atoms of when we're looking at like individual compounds, atoms, they will combine in whole numbers in ratios. For example, water is 2 H's to 1 oxygen atom. You'll never get a situation where you have one, say, iron atom and like 2.5 oxygen atoms. That's just not how it works. So that atoms will always combine in whole numbers and the small ratios. So the simplest ratio you can have. For example, if you have a ratio like 4 to 2, you can always reduce it to 2 to 1, and that will be the simplest form for a compound. So you always go with the smallest ratio and whole numbers to form compounds. So you always see that when we're talking about like chemical formulas, and when we start talking about that, we'll go into more detail when the time comes. Okay. So let's talk about one of the combining laws when we talk about atoms. So let's talk about the law of multiple proportions. So say I have carbon monoxide, very toxic, very toxic thing, but it's very essential or to nature. Actually, it's not very essential to biological organisms because CO actually has a higher affinity than oxygen for hemoglobin. So that's why when you inhale like smoke, like um, like smoke, that's why it feels so powerful because actually carbon monoxide can enter your bloodstream more easily and be attracted to hemoglobin, and it will displace the oxygen. And that's why people die from CO poisoning. But anyway, carbon monoxide, you have one carbon atom, and one oxygen atom. So you can also, so carbon monoxide, when you add the molecular weights of carbon oxygen, they'll be in a ratio of 1:1. And so you can also, so it's a ratio of 1:1, but so the weights will be proportional to the coefficients of carbon monoxide. For example, carbon has a mass of around 12 grams and oxygen has a mass of around 16 grams. So my ratio of the masses will be like, for our carbon will be 12/28. And for, times 100, so that's a little bit below 50. And then you have 16/28 times 100. This will be carbon, will be oxygen. So you can see that their weight percentages are related to the number of atoms you see in a compound. So we only use this times 1 because we only have one carbon atom, but here we can have another 1 times for oxygen atoms. For CO2, it'll look a little bit more different. So carbon dioxide, a greenhouse gas, and currently a big problem for climate change. So we're always trying to make our emissions net neutral. So we're not emitting more carbon dioxide than we're taking in or capturing. So this molecule it's a key molecule. People know it as like something terrible, but it's actually important for converting into other useful molecules. But the thing we're trying to do now is trying to take CO2 away from the atmosphere and to avoid the gradual warming of the Earth's atmosphere. But here CO2 is one carbon atom and 2 oxygen atoms. So here we could say that we have 1 times 12 over. Okay, it won't be 28 now. It will be, let's see. All right, let's see. I don't want to embarrass myself here. So let's just say 28 plus 16 for 44 grams. So it'll be 12/44 times 100 if we were to determine the percent weight of carbon in carbon dioxide. And then we could say 2 times 16/44 times 100. And that will be our percent carbon or percent oxygen here in both of these compounds respectively. So see here that the percent of carbon and carbon dioxide will decrease because we have more mass now, but the percent of oxygen will increase because we're adding an additional oxygen atom. So when we combine these two elements, their weights are proportional of each element are proportional to the ratio of the other elements in its compound formula. So it's a simple ratio of whole numbers. And one thing to keep in mind here is that the particulate level and macroscopic level ratios of combining remain the same. So what this means is that if I have one atom of carbon and one atom of oxygen, they'll combine in a 1-to-1 ratio to give me one atom of carbon monoxide. Say if I have like, for a macroscopic level, it's something you can actually see and weigh out. For example, if I weighed out, we'll learn what this means, but if I weighed out like 5 moles of CO2, well, you wouldn't do that really, that's a lot. But no, let's not say CO2, maybe like 5 moles of sodium chloride. Or say like I have 5 grams of sodium and 5 grams of chlorine gas. And when we talk about macroscopic, we're talking about like molar quantities. So say like 5 moles, sorry, not grams, 5 moles of 5 moles of carbon, and let's say like 5 moles of oxygen gas, right? They'll combine in a ratio, and that will produce, depending on the balanced chemical reaction, either at the least 5 moles of, say, like CO2. So is at the tiny particle level, the atom, size of the atom, and also the macroscopic level, the level that we can see, measure out like carbon, oxygen gas. We can see carbon, solid carbon, but we probably cannot see oxygen. So, but it's basically measuring out like things you can see macroscopically, and that's what we do in the lab, right? We measure out quantities and carry out chemical reactions. So that's the combining in equal proportions applies to both the very small level and the level that we can see. Okay. All right, so now we're going to talk about the electron. Let's talk about the electron. So what is the electron? Everyone should know what the electron is, because that's where electricity comes from. So the electron, when you pay for your electric bill, right, PG&E will keep the power on. And what they're actually sending you is electrons through those cable wires. So when your house is hooked up, it'll have power, a line for power, and those electrons, there's constant charge being supplied to your house that powers everything. So we are thankful for the electron. So subatomic particle. And in chemistry, the electron is everything for chemistry. Subatomic particle carrying a unit negative charge. It has a mass, so you don't need to worry about this too much, but to get you thinking about how small an electron is, it has a mass that is 1 over 1/837 of the mass of a hydrogen nucleus. So that is very small compared to the nucleus. And it's found outside of the atom. Oh, so not outside the atom, but outside of the core of the atom, which is the nucleus. It's found outside the nucleus of the atom. And that explains why it can transform and combine with any other particles, because there's electrons nearby that can kind of interact with electrons of the other, say, atom. So it has a value of -1. So we assign that value because it has a net negative charge. So the symbol we're going to be using for now on is this. Sorry, not symbol. the symbol we use is E subscript minus charge, so electron. So a piece of history for you, discovered by J.J. Thomson. So he's the one who got credit for its discovery. J.J. Thomson. Okay. Okay, let's talk about the history of the electrons, and let's talk about the Plum Pudding Model. So we were talking about electron, right? So how do we know that electrons are there? So here is the Plum Pudding Model. What it states is that this is a model of the atom proposed before discovery of the nucleus. So what this states is that the negatively charged electron particles are embedded within positively charged So what I assumed was that you had like plum pudding, right? It's like this spherical thing with positive charge in it, and that like the plum sticking out of the pudding is these electrons. So that's what we say about plum pudding model. So if you ever get lost of what plum pudding model is, just think about a spherical, like like a bowl pudding, and then you have these like plums or raisins that stick out, and those are your electrons floating within the atom. So that's basically the plum pudding model. And I could draw something that looks like it. But I think there might, hold on. Let me see. Yeah, so that is, for example, if you say like, say this was net positive, right? There's like positive charges everywhere. And then in this, and by the sides are these negative charges, which are the electrons, like point charges right here. Something crudely representing this. But obviously that is not how it came to be, and we're going to discuss that right now. Okay, so now let's switch gears. Let's talk about okay, so hopefully everyone can see this. I think I've shared the right screen. So let's talk about Rutherford's scattering experiments. So if you can see this diagram, what Rutherford did, he shined alpha particles at this piece of gold foil, and the hypothesis was that we're going to determine whether or not atoms are mostly empty space or if there's something right dead in the center. So in this little like screenshot here, you can see that the nucleus would deflect some of the particles, but most of the times these blue arrows, the particles just flew straight through the gold foil and to the sheet right here that picked or detected those experiments. So what he can conclude here is that the atom itself is mostly empty space, but dead at the center is something called the nucleus, which deflected those particles. So That is Rutherford's famous scattering experiment. Okay, so let's go on here. Let's see. Okay, so now let's change gears again. I'm just going to write this. Okay. Come up soon. All right. So from the result of Rutherford's experiments, we now have a picture of what the atom, we have more information to describe a model, because a model is always something we come up with to describe things we can't see from experiments and hypothesis. But we must prove our hypotheses in through experiments to have any weight or value towards the advancement of science. So to that end, we have the nuclear model of the atom based on Rutherford's experiments. So nuclear model of the atom. So of the two theories, I might ask you about Plum Pudding Model. I might ask you about Rutherford. There can be some questions, so definitely do not neglect it or do not put any attention to it. They're very important models to our understanding of the atom. So they may be tested. Okay. So nuclear model of the atom. So what does it state? Every atom contains a small and extremely dense because if it wasn't dense, it'll probably fire straight through the nucleus. So what can we say about the nucleus? It contains the atoms positive charge. So the reason we can state that it contains the atoms positive charge because those alpha particles are actually helium nuclei. So they have protons and neutrons, and protons they are positively charged, right? So when they hit the nucleus of the gold in the gold foil, they'll repel each other, and that's why they deflect towards the away from each other, essentially, right? So it contains the atom's positive charge and nearly all of its mass. And we can say this because at any other point, the particles just passed through the atom, so it didn't confirm that it hit anything. So there's no there's no resistance. So it gives an indication that most of the atom is empty space. So in this case, the major volume of the atom is empty space. And space outside nucleus is thinly populated by electrons. So the space outside the nucleus is sparse, right? So no, it's not sparse. It's very depending on what atom you have, there's space around it, and we say the electrons must be populating around the nucleus, and that kind of gives its orbit, right? Because it's being attracted to the center by a very strong positive charge, so it must be populating around the nucleus throughout the atom. And then we could say the total charge of electrons balances the positive charge of nucleus. Okay, so the total charge of the electrons balances the positive charge of the nucleus, and that's why we get these kind of atoms existence that they're neutral, somewhat stable. Because you can't really isolate ions. We'll talk about what ions are, but ions are basically they're atoms that have lost or gained of electrons, so they become something called ions, and they're very reactive and they react. So they cannot exist by themselves in nature. They're always found in compounds. That's why you never see sodium ion, in nature, or sold on the shelf is always sodium chloride, or some other sodium compound. Okay, so let's move on here. Okay, so the nuclear atom is very small in size. So let's talk about that. Okay, so the nuclear atom. So let's go back to the slide. I think it's a good representation of it. Okay. All right, so you see here the nuclear atom. So, oops, sorry, I went backwards. So the nuclear atom here, the relative sizes of the atom. So look at the this central part here is the nucleus, and it's made of these protons and neutrons. So we can go even further and say what the protons and neutrons are made up of, but we're not going to go too much into that. They're called quarks, but that is not we don't go further back than protons and neutrons, because it's not, I won't say it's not important, it's not applicable to chemistry, but the protons and neutrons are, because they give us these characteristic elements and stuff like that. So you see here the region around it is the electron cloud, and that's where electrons occupy. So they dimly occupy. We'll talk about how they occupy the space around the nucleus, but this picture, it just shows that relative to the whole atom, it's very, very small. So the diameter of the atom is approximately 10,000 times the diameter of the nucleus. The nucleus is a very, very small. So it's about 10 to the negative 14 meters, whereas the atom is about like 100 like picometers. All right, so very, very small. Okay, I think that's enough for the slides. So let's go back to our whiteboard here. Okay, so that's all the pictures I want to show you today. So, okay, so let's erase this. I kind of explained it already. Okay. All right, so let's talk about the results of the experiment, just summarizing them a bit. So combining results of the experiments with the nuclear model. Oops. The nuclear model. the nuclear model. So one, most alpha particles were not deflected. Confirming that most of the atom is empty space. So fractions. So fraction of particles slightly deflected. Slightly deflected as they pass close to the nucleus. So this is important because it tells you that the nucleus is positively charged as they pass close to the nucleus. And then particles near the nucleus, so particles near the nucleus. The particles near the nucleus are repelled by positive electrostatic forces. So what I talked about earlier, positive. So in this case, they're talking about repulsive forces. Electrostatic and then a small number of particles on the collision course with the nuclei were repelled backwards. So this is a lot of information to kind of remember, but I'll just ask you like questions like, oh, like which of these statements is not true, stuff like that. So if you can always relate the particles, the expansion of the particles and how it confirmed that there's a nucleus dead in the center. That's where most of the mass is, and that it's positively charged, and the space around the atom is empty space. I think you'll be okay. So so the last point is talking about that that the nucleus is very small compared it's very small compared to the rest of the atom. So the nuclei is a fraction is a mere fraction of the total volume of the atom. Okay. All right, so let's talk about the last two subatomic particles. So we're going to talk about the rest. Here we go. Subatomic particles. Subatomic particles. So proton. So a proton, it carries a positive charge, a unit of positive charge. And this is found within the nucleus. So think of a proton, like positive charge proton. So this was absolutely discovered by Rutherford because of his experiments. And our symbol is, we denote it as P or P plus. So is that is a symbol for proton. Now neutron, like Jimmy Neutron. So neutron does not mean negatively charged. That is electron. So like think of electron like electric shock, and it will harm you, like lightning. So you can get electrocuted. So it should have a charge on it. Neutron, you should think of neutral and not negative charge. Think neutral. That gets confusing too. I got them confused. I mean, when I first learned chemistry, so I understand. So neutron, electrically neutral. Neutral subatomic particle within the nucleus. So the role of the neutron, I'm not sure what it does. I know the proton's there to kind of keep the electrons in orbit. The neutrons, I think the neutron's role is not merely. No, we're not going to downgrade the neutron's role, but I think it's in part to hold the nucleus together with the proton to maintain the identity of the element. And also, we'll talk about what isotopes are. So basically, those are different number of neutrons, but they will have the same identity of the element. So they're basically like a different type of the element. But they are not the same. They're not the same thing because they have different number of neutrons, and that contributes to the mass of the element. So we'll talk about that. So the neutron definitely plays a role in isotopes, and isotopes have they have many. They have natural occurrences, and they do represent part of the nature of the elements that we see in the world today. So continue off. Electrically neutral subatomic particle within the nucleus. Within the nucleus, its mass. So its mass is approximately equal to that of a proton. Proton, and it was discovered by James Chadwick. But don't worry too much about the discovered, who was discovered by. I rarely ask questions about that. Symbol is, we simply denote it as N or N to the 0 because it has no charge. Okay. We talked about electron already. So just go back to your previous notes. So we went over that. All right, let's talk about isotopes now. Okay. So isotopes. What are isotopes? So isotopes, before we talk about isotopes, let's talk about some few terms. Atomic number. So atomic, hold on, let me just, atomic number. So the atomic number is also called the Z value, and that gives the number of protons. Number of protons in the atom of an element. Guys, don't worry about the new stuff today. The quiz won't be on new stuff. This new stuff will be tested on the midterm. So I'm not all about making a quiz based on stuff we maybe covered a few days earlier, because I know there's a lot of information, so I'm not going to do that. But this will be on the midterm. Okay, number of protons in an atom of an element. So all right, so what we want to pinpoint here is that the total contribution to the mass from protons and electrons is the same for every atom of the element. Every atom of the element. So now, what about the neutrons? What about the neutrons? Okay, that's where isotopes are now being defined. So isotopes. So they are two or more atoms. More atoms of the same element. Of the same element that have different masses. So they will have different masses. So how can they have different masses if their protons and electrons are the same? Well, that we say that the neutrons differ. So they differ. Whoops, that was a very slow refresh rate. So they differ in number of neutrons. Or n value. Okay. So the isotopes are always identified by their mass numbers. For example, carbon 12, carbon 13, carbon 14. You also have nitrogen 14, nitrogen 15, hydrogen 1, hydrogen 2, or hydrogen 3. Hydrogen 3, tritium is very, and we rarely talk about it because it's radioactive. Deuterium is commonly encountered. You may have heard of like deuterated like compounds. That's important in the chemical industry. We won't talk much about deuterium other than that. But what we can say is that they're identified by its mass number. And we'll talk about how to calculate that. Okay, so mass number here is, let me just highlight a few terms here. Mass number, isotopes, atomic number. So just know those definitions. All right. So mass number, or we call it A. So it's the total number of protons and neutrons. Let me rewrite that. And neutrons in the nucleus of the atom. In the nucleus of an atom. Because relative to the protons and neutrons, electrons are very, very small in weight. They're very, and they factor in about like several orders of magnitude smaller. So when we add the contribution from the electrons, they don't change the mass by much or at all, or like in a significant way. So we don't contribute that to the mass number because the protons and the neutrons make up the bulk of the mass in the nucleus. So A equals Z plus N, which is the protons plus the neutrons. Okay, well, I think we're going to do some exercises about this. That's definitely something I like to test. about subatomic particles. Okay. Okay, so let's talk about more isotopes. Um, so, so we're going to talk more here. So let's talk about the naming. Name of an isotope. So how we name it is we have the element, elemental, so name. Sorry, not name. Name. And then we have a dash with the mass number. Let me just check the time. 28 minutes. All right, so here's an example of it. Example, oxygen has 8 protons and 8 neutrons. So how will we represent oxygen? Well, our mass number is number equals 8 plus 8, the sum of the protons and the neutrons. That gives us 16. Let me rewrite that. 16 looks pretty bad here. 16. So the name is, so we name it oxygen 16. Like so. So we can also represent by a nuclear symbol. So you may encounter this in the nomenclature or this denotion by 2 different ways. So we have number of protons plus number of neutrons and here at the bottom we have number of protons again. And here is where we have the symbol SY, that is our symbol. Another way of looking at it is mass number on top and atomic number on the bottom. Like so. And we could denote this with our symbols A and Z, SY. So the bigger number always comes at the top because the mass number has both the protons and the neutrons. Z only has the proton number. So always when you're writing a symbol, always have the bigger number on top. You know you're wrong if you have the bigger number on the bottom. Okay, let's try an example here. Example, what are the nuclear symbols for carbon 12? 12 and carbon 13. So we can list out our symbols here. So we have carbon here, carbon here. We know that carbon 12 is the mass number, so we put the mass number on top. And then we have carbon 13 is the 13 is at the top. So now we just need the proton or atomic number. So let's go to our periodic table. So if we go to our periodic table, we can see that if we look at the carbon, so I will go we're going to go over where carbon is you know, in the future for when we talk about periodic trends. But carbon, the central number beneath the element on the periodic table. So make sure you have a periodic table handy. I will provide one on the quiz, so you'll have it available to view. I mean, if you have a handy one with you, I don't see why that's a problem. But I will provide one just in case no one has a handy one. Has one handy with them. So if we look at carbon, it has an atomic number of 6. So we label 6 here. And remember, in each of our symbols for isotopes, carbon's proton number must be the same. If carbon has a different atomic or proton number, it will be a different element. It will no longer be carbon. So just make sure when we're writing out isotopes, that the bottom value is a 6 or is the same number as the other isotope you may be writing. Okay. All right, let's talk now. Let's do an active exercise. All right, so we're going to be talking about here's another active exercise. I encourage you to do this before looking at the answers. Okay, so what I want you to do is fill in the blank. The following table using the relationship so I will not make you memorize the periodic table. So you need to have one handy to do this exercise. So make sure you do that. All right, let's draw out the table now. So here we're going to have the name of the element. Name of element. Barium. Oxygen. So then we're going to have 2 more rows. Okay, here's the symbol. So elemental symbol, element symbol. Here we're going to have atomic number. So atomic number, that is our Z value. Protons. So this will get you into use to have to naming the elements and how that's all their information. Protons, neutrons, mass number. So mass number or the A value, the value of A. Now we're going to have nuclear symbol. And lastly, name of isotope. Okay. So barium, we're going to draw a line through all here. Oxygen, and the last 2 elements. Okay, let's fill in some more information. 82 for atomic number, 10 neutrons for oxygen. Barium will have a symbol of this. 56. 206 is the mass number for unknown element right here. And here's the identity of the isotope, zinc 66. Okay, so I would say take maybe a few minutes to do this. Have your periodic table ready, maybe have a calculator just to double check your work. But what you should get is the following. Element symbol for barium is Ba. Oxygen, O. This element is actually Pb. We'll talk about what that is. And zinc is right here. So zinc. Pb is lead. It comes from the name plumbate, and that was a common name to refer to lead. So atomic number for barium, 56. Oxygen is 8. Lead is 82. Zinc is dirty. Protons, protons will always match the atomic number. So keep that in mind, 56, 8, 82, 30. Now neutrons, remember we subtract the top mass number from the atomic number. So neutrons here is for barium. Barium we can just subtract the 138 minus the 56 in the symbol. We should get 82. For lead, it is 124. For zinc, it is 36. And that is because zinc 66 is the mass number, so subtract that from 30, 36. Mass number, combined protons and neutrons, 138. 18, so this is oxygen 18, lead 206, and then zinc 66. So here we go. 18.8 for oxygen, 206, 82 for lead. Let me just erase this a little bit. That looks a little bit messy. All right, and then we have zinc right here, 66, 30. And now let's name them. So this is barium 138. Sorry if it's small. I should have myself more room. Oxygen 18. And lastly, lead 206. Lead 206. All right, guys. So hopefully that exercise was okay. If you're still struggling, I will go back and try these again and see if you get the same answers. Just remember, you need to use the atomic number and the mass number and know what those definitions are. Atomic number is the number of protons. Mass number is the number of neutrons and protons combined. All right. So let's move on. So let's see how much time. Okay. So let's talk about the disproved features of Dalton's theory. So the indivisible nature of atoms. So he stated that the atoms cannot be divisible to any other particles or things, or that the atom was just one complete entity, and that that's what all atoms were. So atoms were indivisible by nature. Well, we disproved that by the existence of subatomic particles. So atoms have subatomic particles. Called protons. Neutrons. And electrons. So all atoms. So also to prove that all atoms of an element are identical. Well, this is not true because isotopes are atoms of the same element, atoms of the which have different masses. So isotopes, they exist as well, but they have, so isotopes are like a different type of the same atom, but with a different mass, and that disproves that all atoms of an element are identical. They are not. Okay, so that's Dalton's theory. So next we're going to talk about atomic mass and what that means. Okay, so atomic mass. So atomic mass unit, or AMU, that's the basic unit for measuring mass in for atoms on the atomic scale. However, that's not practical to do in like a laboratory setting, especially for chemistry. If you're not studying particles, if you're studying physics, that is more appropriate. But here we talk about the AMU, or atomic mass unit. So here it is, mass unit. So that is denoted by U, or AMU. One of the two, doesn't matter. It's 1/12 the mass. 1/12 the mass of an atom. An atom of carbon-12. So we say that because we need a baseline to measure this atomic mass unit, so we use the carbon atom. So 1U, what went to 1/12? The mass of one carbon-12 atom. So that is really small. Because the masses of atoms are really, really small. They're on orders below 10 of small, for like the size of kilograms. They're very, very small. You ever looked up, I believe, like the mass of electron is on the order of 10 to the negative 31st power. So it's very small. So taking into account all the protons and neutrons, even so, they are still small compared to like everyday items. So it's working on a very, very small scale. Okay, atomic mass. What do we mean by atomic mass then? So the atomic mass, or the masses you see printed out on the periodic table, it's an average mass. So the average mass of the atoms of an element. Compared with an atom of carbon-12. At exactly 12 atomic units. All right. So don't worry too much about these definitions. I will not require you to know them per se. But these are just definitions we talk about, like how small the mass unit is and how small the atomic mass is for elements. So the average mass of the atoms of an element compared with the atom of carbon-12 at exactly 12 atomic mass units. So 12 atomic mass units will basically be 12 of this value, or basically the mass of one carbon atom. Okay. So you could determine the relative abundance of the different isotopes for an element by taking, for example, a mass spec of a sample of an element, and it'll give you the relative ratios. There is a slide about this, but I'm not going to talk too much about it, but it just gives you an idea about the relative abundance of certain elements, and that the mass you see on the periodic table is much more closer to the isotope in the greater abundance. So that mass will probably be closer to the mass of the isotope that's in greater abundance. But we'll talk more about abundances and what they mean in a problem that we'll talk in I think in a few slides. Okay. So right here, now we're going to talk about it. All right, we have less than 10 minutes left. Okay. So let's talk about active vector size. Number 2. Here we go. Example. All right, the natural distribution so the natural distribution of the isotopes of boron, boron is 19%, boron so it's boron 10, so boron 10 at mass of 10.01 293 9370 atomic units, and 80.1%. Boron 11 at 11.0093055 U. So let's calculate the atomic mass of boron. So how will we do this? So what you want to do is, let's go over this. So you're going to figure out how much weight is the average mass of boron. So what we do is we calculate the factor, so not the factor, the product of the percent of the isotope multiplied by its atomic mass, or multiplied by the mass of the isotope in atomic mass units. So we have 0.199. So always convert to decimal point, or multiply by the percent, then divide by 100 at the end. Because if you don't do either one of those things, you'll get the answer wrong and the number will be really big. So don't do that. So 1.99 times 10. So we're going to keep all the digits. And then our sig figs is going to be limited by our percent, because that's an exact percent number that was reported. So we're going to use 3 sig figs. So 10.01, 293, 70. So we get 1.99 atomic mass units contributed by my boron 10. Now we do the same thing for the 80%, 0.801. So we just move the decimal point from the percentages 2 places back to get our decimal. So that will be times 11.0090, not 90, 93055, and that will give us 8.82U. So then we add those two together. So let's add them together. 1.99 plus 8.82. That should give us 10.8. 1U. So now we have an average atomic mass for boron is 10.8. So we can easily check this. Let's see, Royal. Sorry. Let's check the mass listed for boron on the periodic table. And what we get is 10.81. So that is the atomic mass of boron. So we'll talk about how to. We'll also talk about other mass units for atoms, but that will come at a later time. Okay, let's try this one. So here's part 2. Let's do a different color. And I think this will be where we'll end. Naturally occurring lithium is composed of 2 isotopes. .59% at 6.015, 1224, and 92.41% at 0.01, 600, 41 atomic mass units. So let's determine the atomic mass of lithium. So what we do is we just do the same thing. We're going to multiply. So we have 0.00759. Oh, not 00. Just 10. Let's do that right now. 0.0759, because we moved the decimal points 2 places, times 6.0151, 224. And that gives us a number, but let's just check up. Let's write the other one first, then we can calculate them both at the same time. Then we have 0.9241 times 7.0160041. Let's calculate what those two values should be. So let's get out our calculator and do the following. 0.0759 times 6.0151224. That gives us, let's leave it as 3 sig figs. We have 0.457 U. And then the next one, 0.9241 times 7.0160041. that gives us 6.48U. Now let's combine 6.48 plus 0.457, and that will give us 6.94U. All right, now let's check that number with the atomic number for lithium on the periodic table. And we get 6.94. So that's exactly what we see on the periodic table. So as we can see here, that we can measure the percent abundance of these elements by using something called a mass spec. It'll give you the relative abundance of, say, isotopes of the elements. And so don't worry about the instrument, but just know that we can measure the relative abundance percentages, and we can plot the mass of the isotopes, and we can get kind of like a pie chart or bar graph of the relative abundances for each isotope. So so this is the example of a percent isotope question. So these are ones I like to ask too. So you can expect it probably on the midterm, not for a quiz. Don't worry about that. But anyway, guys, that's it for today. I will send an email announcement soon about the quiz and how it will work. So stay tuned for that. I'm going to be working on that most likely today. But if there's any questions, write up a question on Piazza or email me if it's really urgent. All right, guys. See ya.